All right, well, good morning or good evening, depending on where you're joining us from. We have students coming in from all across Canada, the States, India, and more, so welcome into all of you. My name is Jesse, and I am with Exploring by the Seat of Your Pants. If you're joining us for the first time, and I know we do have a few groups joining us today for the first time, we're all about bringing conservation, adventure, and science into classrooms around the world. So November is our month dedicated to conservation. We've got all these crazy sessions in Indonesia, and Borneo, and the North, and Africa, all these amazing places highlighting species from around the globe. But today's talk has absolutely nothing to do with that. We're going completely off brand in November for a really exciting presentation, and one with someone that we've had on for several years now on the broadcast, Dr. Erica Caden. So we're going to learn about SNOLAB, the Sudbury Neutrino Observatory Laboratory. It's one of the elite research facilities in the world, probing the darkest mysteries of the universe. So we're going to hear from Dr. Caden all about the amazing work that she gets to do, all about the amazing facility, and then take your questions at the end. So if you're in YouTube, let me know where you're joining from, share questions, and we'll take as many as we can. And of course, our live groups, I can't wait to hear from you as well. Without further ado, thank you for joining us, Dr. Caden. Take us away.
Hi, thanks for having me, Jesse. Yes, so physically test conservation laws. Maybe this is how we can fit in for November?
Maybe, I like it.
So right now I'm working from home, but the slides I have up are some pictures of me working at the lab. So the comically large wrench is actually a tool that we use, but it makes for a great prop for photos as well. So I work at SNOLAB, which is, as Jesse said, a research facility. We are in Northern Ontario in Sudbury. This is not quite what it looks like at the moment, but we're closely approaching winter. So where we are, you can see where the purple dot is. Oh, I can see my mouse. And we study dark matter and neutrinos are our primary focuses at the lab. So where I showed you before was the surface building, but the heart of SNOLAB is really underground in the underground lab here. So we operate in an active nickel mine. So Sudbury is the nickel city. There's many nickel mines around, and we happen to be located in Creighton mine, which has been operating for over 100 years. If you go down a very big, very long elevator to the 6,800 level, 6,800 feet, or just over 2 kilometers underground, and then walk another kilometer and a half, or just under a mile, you then reach our clean lab. So this is another image of the lab facility. So because we are a clean lab, and we've just walked through a very dirty mine, you have to shower as soon as you get into the lab to wash all of the mine dust off of you so that it does not contaminate our experiments. So I work on a couple of different projects at the lab. Here is one of them called SNO+, and this is a multi-purpose neutrino detector. There are a number of dark matter experiments kind of scattered throughout the lab, and we have one last unfilled cavern. So in this image, it looks like we have a detector in it, but not yet, and we are planning to build the next generation experiment to study a process called neutrinoless double beta decay, which is a really cool reaction, if possible, that can tell us a lot about neutrinos. But I'm going to kind of back up a bit and start with a standard model of particle physics, or the standard model of the Marvel Cinematic Universe. These are the comic representations of the different fundamental particles. So we have our quarks here, our bosons, our force carriers here, fission is the Higgs, but what I like to study are the neutrinos and Rocket Raccoon. And this is all taken from Claire Lee, who is an amazing science communicator based at CERN. So one of the cool things about neutrinos, so they're fundamental particles, they're in our standard model. You see here that we have the different properties of the particles. Neutrinos, they don't have a mass listed here. And this then leads to, we know that they have a small amount of mass, but we don't know exactly how much it is. And we know that they have a small amount of mass because as they travel from where they are produced, either maybe in the sun, maybe in the core of a nuclear reactor, they change what kind they are as they travel through space. So you see I have three rockets here in different colors. If instead of a rocket raccoon, you have, say, a pigeon, and a neutrino is created in its pigeon state. as it travels through space, it now turns into a parrot. It changes what it is. It changes its own state. So you go from pigeon to parrot, and it's flying along. It says, "Oh, okay, cool. I am now a parrot instead of a pigeon. I have different colors. I have I interact differently in the world around me." And you travel even farther along through space, and you become an eagle. Like, man, this is the best. I am an eagle. Until you then change into parrot and pigeon and eagle, and pigeon and parrot and eagle, and back and forth as you're traveling through space. And this is one of the best descriptions I can come up with of how a neutrino changes as it travels through space. And this is just one of the fundamental properties of neutrinos. And neutrinos, the only particles that really do this on this scale, which makes them so interesting to us. It makes them difficult to detect because you have to design your detector to only detect either eagles or parrots or pigeons. You can't just have a general bird detector. And they're just very different than all of the other particles that we have. So another interesting property about neutrinos is that we have particles and we have antiparticles, and we understand this relatively well. So there you can have a nucleus in an element, in certain elements, certain isotopes, decay into the nucleus of another element. This happens all the time. This is not weird. What's weird is that sometimes for certain isotopes of certain elements, you have these two neutrons inside the nucleus decay at the same time into two protons. And this releases two electrons and two antineutrinos. Oh, so this can happen for a handful of different isotopes. It's called double beta decay instead of a single beta decay, because you get two electrons or beta particles out of it. Now, what's interesting about neutrinos is because of their combination of quantum numbers, which were some of the other numbers in the big chart, you could possibly have a neutrino turn into an antineutrino turn into a neutrino. So whenever you have this decay, instead of getting two antineutrinos out, they self-annihilate inside the nucleus, and you only get two electrons out. And so this breaks the conservation law of lepton number conservation, which is a fundamental physics law. And it's super cool because only neutrinos might be able to do this. We have not yet seen this reaction. This we've observed for a number of isotopes, the two neutrino decay. But to not get any neutrinos out, to only have all of the energy of this decay go into the electrons, to not see the neutrinos would tell us so much more about the neutrinos and about breaking fundamental physics laws, breaking these conservation laws that we hold so dear that build our model of physics. So this is one of the reactions that many experiments all over the world are looking for. And there is one that is being constructed right now at SNOLAB that I work on called SNO+. And there is another experiment, a couple of experiments that are trying to come to SNOLAB, depending on funding situations, to look for this in different isotopes so we can have confirmation that it's not just one detector seeing something weird. So neutrinos have all these interesting properties that we're trying to study. So our neutrino sources come from the sun, they come from nuclear reactors, and they can come from beta decay from just normal particle decays. Neutrinos fly out, and they're not shown here. But it's not just the properties of neutrinos that we want to study. They can tell us about their sources and about where they came from. So we can learn about the fusion process in the sun from studying its neutrinos. We can learn about how supernovas explode and form and their whole ejection mechanisms from studying the neutrinos that come from them. And we can understand our own planet, the Earth, better by studying its neutrinos and understanding the mechanisms for how the Earth generates its own heat. All of our heat is not just from the sun. We generate our own heat, but we have very rough models on how this happens because we can only dig down and test samples inside the Earth so far. But if we can study the neutrinos that are produced from these decays, from these beta decays inside the Earth, and in different places on the Earth, then we can have a better understanding of the heat that's produced. So neutrinos, we can study their own properties, and we can study them as messengers of what they tell us about the stars and the cosmos and our planet. So this is an image. This is an actual photograph of the one experiment that I work on called SNO+. And we are in the process of changing the detector medium from water to a special mineral oil that is inside this acrylic vessel. So it is held up by these ropes here, and then it's going to be held down when it's filled with oil. And we are using this detector, this beautiful piece of equipment, to study if the neutrino is the same as its antineutrino. And we are using the HALO experiment to study supernovas. So this is a dedicated supernova detector. It doesn't have any other physics goals. It just has to be up and watch for a supernova. And I believe at this point in time, it's the only dedicated supernova detector in the world. And it's so cool because the way that it's run and made from some kind of spare parts, and the scientists who built this were able to build a detector that's so reliable and has so much uptime, because we don't know when we're going to see a supernova. So this guy needs to always be on, always be running, and just waiting there and in preparation for getting this data. So in addition to studying the neutrinos at SNOLAB, we also study dark matter. And we just missed, we should have been on last month for Dark Matter Month, where we try to have a lot of outreach and explain about the spookiest particle in the universe, the dark matter particle. So dark matter is it's like this invisible space glue that holds the galaxies together. So we know that as galaxies spin, that the stars on the outside spin fast, and they want to fly off, and they actually spin a lot faster than we expect them to be just from the mechanics of the galaxy. So it's like if you're spinning on a merry-go-round carousel and you have to hold on really tight to the bars as you're spinning faster and faster, the dark matter is like you holding on really tight. The stars should be spinning off, but they're not. They're staying in. So it's the force, that gravitational force of this stuff that we can't see that is holding the stars into the galaxy. So we can see the effects of it, but we haven't actually seen dark matter yet. We can see how it bends light, as in this galaxy. It's kind of sometimes called the Cheshire Cat, because it looks like a mysterious smile. We can see how the light is bent around from these galaxies that would normally be just dots, but the dark matter in the center of this is bending these galaxies, the light, because they exist behind it from the vantage point of this picture. So again, we can see how it bends light, we can see how it holds the galaxies together, but we don't know what it is yet. So we think that we are flying through a disk of dark matter all of the time. So we have at SNOLAB lots of detectors set up to try and catch one of these particles that are flying through us. Neutrinos are flying through us all the time. Dark matter is flying through us all the time. It never interacts in our body, or maybe rarely, but it wouldn't produce anything, it wouldn't make any difference. So now we have to come up with clever ways to try and catch these particles. So if you're a rather grumpy, perturbed dark matter particle, because you like just flying through things, you don't want to be caught, then maybe SNOLAB isn't the place for you, because we have many different experiments trying to catch dark matter. This is a picture of the deep detector that uses argon, which is a gas that makes up 1% of our atmosphere. They have condensed it down into a liquid form and are trying to catch dark matter. We have a News G, which is filled with, I believe, neon right now, or it's going to be filled with neon, to also catch, to see a dark matter particle passing through and ionizing, or hitting an atom that will then ionize. We have PICO, which is a bubble chamber, which is very old detector technology that they have revamped and filled with some other refrigerator fluids to try and see a bubble that would be produced by a dark matter particle hitting into this super pressurized liquid. We have super CDMS, which uses crystals of germanium and silicon to see a dark matter particle, again, knock off an electron and create an electron hole pair and ionize and detect dark matter that way. And we have DAMIC, which uses CCDs, the same kind of light detectors that are in your cell phone camera, to see if the dark matter particle flies through and creates an image on their detectors, their sensors. So we have many different ways to try and detect dark matter, and some of these experiments have been running for a very long time, and we still don't know what it is yet. It's very exciting as we keep chipping away in what we think it is, and how the theorists can say, okay, well, maybe you should look here. Maybe you should try this kind of detector. The experimentalists build the detectors and develop all kinds of technology in the process, and then we still can't find it. So it's exciting to know that there's still things that we don't know, and that's one of the things that motivates me as a scientist. So normally when I give these talks, I'm in the lab and I have you can kind of see the people working around me. So instead, I thought show a picture of Jesse and of Joe and George, who run Exploring by the Seat of Your Pants. So to find out more about any of the topics I've just talked about, in addition to the questions, you can check us out on Facebook, Twitter, and Instagram at SNOLAB Science.
Fantastic. Thanks so much, Erica. So yeah, if you want to end screen share so you can see us again, that would be awesome. Thanks for a really neat presentation. And welcome into students from all over the world. Again, we've got over 150 students from Tamil Nadu in southern India. So welcome into Lady Doak College students, Miss Neely's class in Kincardine, and our live groups. If you're on YouTube and you want to start sharing questions in the chat bar, please do. I'm going to take as many as I can over the next 20 minutes or so. Before we go with Mr. Tunnard and our Fort Langley students in BC, I just want to start off with a question myself, which is, how did you get interested in this? Like, what drove you to this career path? Is it such a unique and fascinating thing you get to do?
So I studied, I thought physics was cool in high school. I had one class. And so then when I got to university, I thought, okay, this excites me. This is something that is difficult and challenging. And I think maybe this is what I want to do. So my advisor in undergrad was great, and it was a small liberal arts school, but they had a pretty dedicated physics department, and the particle class in undergrad was taught by an experimentalist who had worked on accelerators, and the whole process kind of showed me, like, ooh, I think I'd like to keep studying this. So I went to Drexel University in Philadelphia for my grad school, and the particle physics that they did there was neutrinos. So I kind of stumbled into neutrinos, but again, being able to work physically on the detectors and to build things and then do the data analysis, that just expanded everything. And it was so much fun working in these big groups of people. So one of the things that I like about particle physics, and especially about experimental neutrino projects, are that it's not just one person building these projects or doing anything. You're in this big group of people. Sometimes that's 20 people, sometimes that's like 100 people.
Yeah.
But having the chance to interact with people is part of what I like so much about doing this. And also working on studying these particles that are different. There's still so many questions about. We're not just trying to, get down to a few more significant digits in a measurement. We're trying to answer big questions. Yeah. That's the thing.
Fantastic, Erica. All right, Mr. Tunnard's class, they're gifted grade 8s joining us in Oshawa. Mr. Tunnard, if you want to demute your microphone, come on into your class. You're good to go.
Hi. Well, thank you for sharing this experience with us. It's fantastic. Let me just pop over to my other thing to see if there's any of my guys having a question specifically. I guess my big question is looking at my students and trying to think about sort of paths that they're taking. If anyone is interested in science, and maybe not even necessarily neutrinos and what you guys are working on, but any path, what kind of recommendations do you have for them? What kind of things should they be looking at or exploring?
So one of the key things that we do is a lot of computer work, a lot of data analysis. So being familiar with writing code and getting familiar with that early is something that I cannot stress enough will make everything easier. So in my science, we use a lot of C++ and a lot of Python. So learning that, but really just getting comfortable with the concepts and describing the algorithms that way. That's really useful. And as much as we're doing science, there's still a lot of writing and there's a lot of communicating. So certainly in any field, you have to publish papers and give talks and presentations. So being comfortable with those skills and stretching yourself to learn more about writing and presenting, that's something that I think is you can't do enough of. And finding questions that maybe your professors can't answer, and growing and learning from them and going off on your own and trying to answer the question. Yeah. I think
those are great answers. That's fantastic. And again, if you think of anything else throughout the broadcast, anything that's been really impactful for you or in your own journey to where you are, please do share. I do want to mention hello to the Pitatelli family just joining us in Vancouver. So I'll come to you guys in a minute for a question. Miss Way's class on YouTube, welcome into you guys as well. The more the merrier. This is great. Let's head to the Mass family in Fort Langley, BC. If you guys have a question for us, come on in.
Okay, go ahead, Ann. What has been your favorite project and why?
So the projects that I work on, they're big experiments. They take years to build and years to do data analysis. I think the project that I'm just getting started on is called Nexo, and it's another neutrinoless double beta decay experiment. And it's the first one that I've been in kind of from the early stages. So we're still doing a lot of the conceptual design and seeing everything kind of from the ground up isn't something I've been able to do before. So this has been a great learning experience on that. But I think really any time that I get to kind of lead a small group in putting together a small part of the experiment that will then contribute in a larger way, but to feel in a good way that we are like a cog in a wheel, that we are this one piece, but without this one piece, everything would break. That's a really fun feeling.
Very cool. Thanks, Erica. I want to pass along something too. You mentioned this in your last answer. You talked about coding as being something that's really integral. And when I was a kid, coding workshops, coding did not exist. This was not a thing people were doing in any serious way. And now in Canada, at the very least, Kids Code Jeunesse for all our students in Canada is an amazing organization. Chapters all over Canada, incredible workshops, incredible programs. So check them out if you want to get those sort of skills. But they're doing really, really cool work. All right, Pitatelli family, come on in. Just demute your mic and you're good to go for a question. Guys. Hey. Oh, your mic's demuted, but for whatever reason, it's still not working where we can't hear you. So smack the computer really fervently, or worst case, you can type in the chat bar. So on the chat, right on the side of your screen, you can type there. We'll take your questions that way. I'm sorry if it's giving you trouble. Muck with it. I will come back later to see if we can get you guys audibly, but in the meantime, type there. I'll take a question from Miss Way's class while we're waiting. So in Miss Way's class, Isaac wants to know, if we manage to catch dark matter, will there be any consequences? Very foreboding, Erica.
Consequences. I mean, maybe the consequences of lots of papers coming out that we all get to read. The consequences of... So we'll then have to make sure that what we see is actually what we think we see. So we are very careful in building our detectors to make sure to minimize the things that can cause a signal that will look like the dark matter particle and trick us. So we have to remove as many of those sources from the detector. So this means being careful about the materials that we use and being as clean as possible when we are building them. But also when we can't remove those materials, to make sure that we model them and we understand them in our detector simulations to know that, okay, I couldn't get rid of this piece of equipment. So it will probably cause 6 events over the course of the lifetime of the experiment. So we know that we'll have 6 events that look like dark matter, but aren't dark matter. So to understanding that and really well modeling our experiment is very important. I realized another thing that was important in my development as a scientist that I didn't mention earlier is mentorship. And I have had many scientists, many mentors that I have been able to look up to and talk to and ask questions of, science questions, but also life questions and the process of being a scientist questions. And that has been very important. So finding a mentor, finding someone who you can relate to and who will help answer your questions during the whole process, that I don't think I would be where I am without the people that I relied on.
Fantastic. So speaking of sort of tools and tricks to help you get where you are, thanks, Julia, for the great question in the chat. So you talked about coding for kids and how for them to get involved in learning coding. She's off to university next year and wants to know about coding courses for someone who's not too familiar with coding would be a great addition to a science degree. Are there courses you can take? Are there courses you'd recommend? How would you go about learning coding and sort of formal versus informal education?
So most of mine had been probably more formal. It was in classes in university, and then in working with my classmates. So again, realizing that this is not a solitary stream, that you are not the only person who is solving these problems. And you obviously there's academic integrity and no copying off each other, but you can still help each other and sharing resources and kind of looking over someone's code and trying to find bugs and figure out different ways to do things. There are many resources online for questions, different tutorials for different languages, and every language has its own kind of quirks. So learning many language, but still learning the overall philosophies of coding and understanding kind of how lists work and how if statements work, and now getting more into machine learning techniques, which is a lot of what we're doing with our big data sets that I've never done personally, but that is a lot of where the future is going in some of these analyses and trying to disentangle certain parameters.
Yeah. Awesome, Erica. All right, I'm going to take one question from YouTube, and then we'll go back through with all our live groups one more time at least. So Miss Neely's class, grade 7s, they want to know, are there other mines that you've worked in? Have you been to other research labs around the world other than SNOLAB?
So I have visited other labs. There's an accelerator lab just outside of Chicago, Illinois called Fermilab, and they are building they're upgrading their accelerator, and all the way out in South Dakota, they're building a new detector to shoot neutrinos through the earth from Chicago to South Dakota and to see how they change, again, from the pigeon to the parrot to the eagle as they fly through the earth, and how the earth can change and affect that change process. So Fermilab is a great lab. The experiment that I worked on for my PhD was actually at a nuclear reactor facility. So when I showed the picture of the nuclear reactor cores, that's the one that I worked on, or that's the reactor complex where my experiment was. There is a lab in Bulby Mine in the UK. I believe there is a lab in I think it's called Sidwell in Australia. There's a lab at the Waste Isolation Process Plant in New Mexico in America. there are a few locations. There's actually a lab underneath the Alps I'm sorry, maybe not the Alps, but in Italy underneath a mountain. And there's one in China that's underneath the mountain too. So we can go, we go deep underground to stop cosmic radiation interfering with our detectors. So you can go straight down through a mine, or you can go sideways through a mountain. And there's pros and cons to both.
Sounds like a Bond villain lab, like, you know, the secret layer inside the mountain where you do science with like these giant orb things. Very cool. Mr. Tunnard, you shared on chat, but let's go live to you and you can share the question from Suha. I'd love to hear it in person.
Well, I don't have her. I can't actually get her on the.
You can share it with us.
Yeah. So so she's posted. My class is posting questions for me. So she wanted to know, will dark matter particles last long enough to be studied, and how long, and how will they be preserved?
Yeah.
So that's a great question, because with all these particles, as they interact in our detector, most of the time they're destroyed. So actually dark matter will probably bounce off a nucleus and again, just keep going, keep scattering on. But as the nucleus then kind of bounces around, it creates light. So we don't see the particle itself. Again, we see how it interacts, and we will hopefully know that interaction is caused just by a dark matter particle and not by something else. So then we study this interaction. We study the light that is produced from the bounce, and that will tell us about what made it bounce, if that makes sense. So it's not like catching a fly and studying a fly. It's kind of seeing how you're still studying the reaction.
Yeah. And with like these detectors, it's so astonishing the degree of precision of what they're able to capture in things like the Large Hadron Collider, in SNOLAB. I mean, it's the infinitesimal amounts of energy or information that are being conveyed. It's incredible. It's like seeing in astrophysics, same sort of idea. You're talking about things like seeing like a candle on the moon. Like if someone were to flash a candle or flash a flashlight at you for a quarter second, that's what we're capturing. It's not like these big flashes, not a ton of information. That's why these detectors have to be so sensitive. That's why they have to be so elegantly designed. And it's a really, really exciting science. So thanks, Erica. All right, Fort Langley, let's go back to you guys, the Mass family. If you guys have another, come on up.
Hi, my name is Luca, and I'm wondering if you also study dark energy, and if you do, what exactly is dark energy?
The dark energy question. I was waiting for that one. Thanks, man.
So we don't study dark energy, but that is one of the things that we don't really know that is causing the expansion of the universe and the acceleration of that expansion. So there are other cameras and astrophysics experiments that are studying that, but that is one thing that we don't do at SNOLAB.
There you go.
Sorry.
That's okay. There's some really, really cool popular science books that start being accessible for sort of grade 8s and up that I would say that talk about dark energy, dark matter in a really detailed way. It's really quite fascinating to think what percentage of the universe we really don't understand on a fundamental level. So much. Is it 94%, 96%?
Yeah, I would say about 95%. So yeah, 95 to 96. Everything that we see, all of the stars, all of the planets, everything around us is 5% of the universe.
Great. I mean, it's fascinating and disconcerting at the same time. It's very, very odd to think about. So very cool question, guys. All right, Pizzatelli family, you guys asked some great ones in the chat. I want to take a few from YouTube first. So this is a question from our friends in Lady Doak College and from Mr. Tunnard's student, but I'll take it from our student, Akshaya. Is your job at SNOLAB more focused on building dark matter detectors or more research-based, Erica?
So it's both, which is one of the great things about working at a big lab like SNOLAB. So I get to be part of the teams that build the detectors, and I enjoy the wrench turning aspect, but it's also the design and the research and development of some of the different parts that go into them. And then it's the making sure that they keep running and that they are taking data in a way and that data is good and analyzable. And then analyzing that data to get the answers out and analyzing all of the different pieces that show that we do understand our detector. There's so many parts to it, which is why that no one person could do it. and that and knowing that we're all working as a team together, that we're all relying on each other and are responsible to each other and for each other for making all of these parts work. And I really like being on site and doing the hardware work. I find that very very fun and very rewarding.
Yeah, I know it doesn't allow for it right now necessarily, but it's really exciting if any of our students can tune in for another broadcast with the AR group. Is usually she's down in SNOLAB with the hard hat in the facility. Super, super cool to see. So hopefully you get that opportunity later next year, maybe sometime.
We can make it happen.
Sorry?
We can probably make it happen again. I could get through all the pandemic. We've still maintained presence underground, and you know, if you have a good enough reason, you know, to work whichever project you're working on to get underground. So I think we could make it happen again.
Okay, well, we'll hold you to that. We'll call you later. 2 more questions before we wrap up. So one question we've gotten from a few people on YouTube now is about antimatter. Some of us have heard of antimatter. We think about it. What is going on with antimatter? What is it for people who don't know? And do you try and detect it at SNOLAB in any way?
So the yes, kind of. So antimatter is then just kind of the opposite of matter. So you have an electron and you have a positron, which is just a positively charged electron. And they're not the kind that when we have atoms and the electrons flying around, they're all negatively charged. But you can create, it's not impossible to create you know, the positron. So we have neutrinos and we have antineutrinos, and they really are produced depending on the reaction in almost equal amounts, and it all depends on the reaction. So nuclear reactors produce antineutrinos, and those are ones that we detect in our detector from the nuclear reactors in Bruce and Darlington and Pickering, those reactor complexes. So that's antimatter that we study, but we can also detect neutrinos, not antineutrinos, that are produced in the sun. So the sun makes neutrinos. Nuclear reactors and the Earth make antineutrinos. And accelerators, you can make both depending on how you tweak some settings. So we do study antimatter, but that's also a thing that is studied in some big collider experiments as well.
I'm muted. I should know better than that. I do this for a living. I'm going to bring this question into a banner because I love it, from the Pizzatelli family. So I'll just wave and say hi to you guys again. You've had some great questions. I'm going to wrap up with your 2, which are fantastic. So this one is really, really personal. I really like it. Do you ever find that being a small cog in a larger picture is ever frustrating, as you rarely see the end product? So this is something where the science can last many decades. It can be an international collaboration. Is this something that's personally troubling, personally interesting to you? Anything you can share? It's a really unique question.
No, that's a great question. So I've been lucky enough that a lot of the experiments that I've done have lasted a number of years. I've also been working on them for years. So I've seen some of the growth, and I've seen results along the way. And that's one of the nice things about the field, is that it's small enough that you can still keep in touch with the projects that you're no longer working on. Do I find being small cog frustrating? I don't, because I know that the parts that I'm working on are still vital, and they are, like, the rest of the experiment still couldn't go on without them. It would be nice sometimes to be involved in more areas, but this is a good question. I don't think I've gotten this question before. No. I see how it can be frustrating if you don't see the effects of what you're working on. But I think this is then another piece where having strong mentorship can come into it. If the people that you're working with on your project can help to reassure you of the effect that you're having. That, I think that's why I haven't come into that problem yet. So if you're feeling that way on what you're working on, definitely talk to someone about it. Yeah. And that helps everything.
Very cool. Great answer. Great question, guys. And I want to wrap up. You talked about sort of value to yourself personally? And I think this is a really nice question to wrap. And I challenge you to be as concise with this as possible, because it's a big question. It is, what value does this research have for future generations? I'm sure it's a question you've got many times, and we've had it in all our broadcasts. I know. Why does this matter?
So this matters for I like to kind of break it down into 3 different reasons. Understanding the universe around us matters. It's knowing how everything came to be. Like what are the processes that made the stars, that made the planets, that created things, that let things be created in this way? How that happens? That's important to understand. So that is worthy of studying. Number 2, the technology that we develop has much larger overarching effects than just our detectors. So a lot of our detectors have ultra clean fluids, and there's a lot of gas handling to help keep these fluids pure and cold in a lot of senses. So a lot of our experiments are cryogenic. So we have a lot of experience with pressure systems. This came in handy when in March, when in North America, and February in Europe, when everything happened with COVID-19 and the pandemic, and there was this huge need for ventilators. The particle physicists working in Italy and in Canada and in the US teamed together to develop a new kind of ventilator because of their experience in pressure systems and gas handling that was used off-the-shelf parts and had a mechanical, computerized mechanical interface to help regulate breathing, to help people breathe either when they are unable to breathe on their own, or if they just need some assistance in breathing. So we were able to use our skills and our knowledge to create something, and this has been approved by Health Canada, and this has been approved by the FDA, and it is in production in Canada, and I believe it's nearing production in the States. So that's another way that we've been able to contribute. So that's using our technology, in addition to particle physics. Physicists created the internet, and a lot of non-invasive cancer therapy techniques. Proton therapy has been taken from accelerator technology.
Yeah. So
there's answering the big questions. There's the technology that we develop, and there's also the people that we develop. Not everyone is going to go on to be a professor or to be a research scientist, and that's great. That is wonderful, because we need people with the analytical skills and the computer skills and the ability to ask and understand these big questions in so many other fields. I have friends who work in Health Canada doing data analysis on health data, and in other analyzing big data sets for health questions, financial markets, and that big data analysis. In teaching, and there's so many skills that you learn in studying physics that are so useful in so many other ways. So we answer the big questions, we create great technology, and we create highly qualified people who are able to then go off and study other things. So that's what physics has done for you lately.
That's what physics has done. Erica, that was fantastic. Thank you so much for sharing all your stories and answering all these amazing questions today. Some really poignant questions. So thank you to our live families, our groups joining on YouTube. And as you know, what we do at the end of every broadcast, I'm going to bring in everyone. So Mr. Tunnard, our Fort Langley group, and the Pizzatelli family, join me in saying a big thank you and goodbye to Erica. Thanks